Hello, my name is Mauricio. I will present the longest common substring problem in big O of n time. Uh, so the this is the overview of my presentation. I will give an introduction to the problem. Then I introduce suffix tree, the generalized suffix tree, largest common substring from the suffix tree. And then I will introduce the suffix array and how we build a suffix array in O of n and big O of n time, linear time. Then I will introduce the LCP array and 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 how to build it in linear time using Kasai's algorithm. I will conclude, and so let's start. So what's the longest common substring problem? The longest common substring problem is to find, as the name say, a substring, which is a sequence of characters. It's not like a subsequence. It's they must be contiguous sequence of characters, and we need to find, given given two strings, I need to find the longest substring that occur on both strings. Uh, the naive approach using dynamic programming would take O of big O of n square time. We just compute for each. We compute the algorithm would be like compute the longest common substring uh, ending at the position j for each of the strings. So if both are of size n, it would have like n square time. A similar problem is the longest substring that occurs twice in the same string of length n, and this kind of string problems and structures and trees and structures was a major stringology probably. So many researchers try to solve this kind of problems, and many different attempts, and sometimes this conjecture, not conjecture that the lower bound for this type of problem were n log n, and some and many people believe that that was in fact the lower bound. But we know now that the solution is, we can have a solution linear time, and so let's talk about it. For talking about it, let's first introduce the suffix tree. Suffix tree. Uh, let's take, for example, this word banana, and list here all the suffix of the word banana. Let's put an end, an end mark here in banana, and this and so we have like we let's give a number for each of the suffix. This is, some start from 0, some start from 1, but let's assume that starts from 0. So the suffix 0 would be the one that starts at the position 0. The 1 and 2, 3, 4, 5, 6, and so far, so on. So these are the 6 possible suffixes of the word banana, and we will arrange them in a tree like that. So for each suffix, we start from the root, and from the root we can go, uh, it's not here, but we can go to 6, um, and then there's what's the possible way to start a suffix. So we can have like an and from A we can either end at A, so this A end with 5, or we can go after an A, go to NA in this case, and also in this case, or we can start with a B from the root level. We can start with a B, and the only suffix that start with B is banana, so all the way banana to the suffix 0. And there are also the possibility of starting with N, and they all suffixes that start with N in fact start with Na, which is the 4 and the fourth and second uh, suffix, and the fourth ends with an A, and the second has an additional NA, so it's shown here. So this is the suffix tree, and this is how um, this is a structure that um, has many uh, applications, and this is another suffix for the word Mississippi. And some concepts of the suffix tree are, if you take the leaf nodes, uh, if a word has, let's say in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, uh, the n is 11, then there will be 11 leaf nodes, and for each node there might be as many children, direct children, uh, as the alphabet size, because to each path, like S, FS, I can have uh, any of alphabet next letter as a children of this any specific node. Uh, so the alphabet size plays a role here on the number of children a node can have. There's some concepts like string depth. What's the string depth? As each edge is labeled by the sequence of of characters to go to this. The string depth is the number of, for example, for this node, the number of characters on the path label. The path label is the sequence from the root to that node. So the path label is SSI, and because it goes to the edge S and SI, and the string depth for this is 3, 1, 2, 3. So what are the applications of a suffix tree? There's many applications. One of these application. Imagine that you built this for DNA sequence, for a huge DNA sequence, and you want to find a small sequence. So find a small string in huge strings can be done, because I can find, I can, starting from this, I can go and do, once the suffix tree is built, it's assume it's prior built, and you find small strings proportional to the size of the small string, not to the huge string you have. So this is one of the application. Another application is length of zip compression. The length of zip compression does in a similar way. It's whenever it sees a sequence of a sequence that was already seen before, it reference that thing, that sequence, instead of repeating it. So, as in our in English or in DNA, there's a lot of repetition of some sequence. Uh, this this turns out that we can get a good compression using this method. Um, and it's obvious that this is a good application because we can uh, identify the sequence that we have already seen uh, from this suffix tree. Um, Another application would be the subject of this presentation, is the longest common substring. So if you have if you have a suffix tree, we can find the longest common substring. But for that, we need to introduce first the generalized suffix tree. What's a generalized suffix tree? Is a suffix tree for not a single but multiple strings. Let's say we have like three strings: A B and B, B A B A, and A B B A. And for keeping them, um, for knowing, we just end them with different markers, and this is the $0, $1, and $2. Two different, three different marks, because in this case it's three string. Uh, and then I know, like, uh, going starting from the root, there's some suffix that start with the A. All suffixes that start with A will be on this side of the tree. And then and then let's say A, and then all suffix that end with this suffix A and is seen in string 1 and string 2. So you can see string 1 ends with A, and string 2 also ends with A. And we can see like the sequence A and then B, a suffix that start with A, B, and has an additional A. There's two suffix that has this. One is one string one, and the other on string 0. Uh, and they start on the position 1 and 0. So yeah, if you see this, the ABA is seen here, and the ABA is seen here as well. So that's what this represents, is a way to represent multiple strings, one, two, or n strings, in the same suffix tree. And by the root node, we know, um, by the root leaves, the leaf nodes, we can say uh, from which string that suffix is, if that suffix is present in which string. But we represent all the suffix that are present in all the strings with this thing. And with this generalized suffix tree, we can see that we can get the longest common substring using the suffix tree in a easy way. The common let's say that here is the suffix tree for AB and BA, and and we want to get the longest common substring of this. So the longest common substring of from a generalized suffix tree is simply the deepest internal node that have leaf nodes from all the substring. Uh, so let's say, how do I get that? I do a button up traversal, and then I find like for this one, let's say I get this node here. It's and I mark every node that I go with the the strings that the string number that is that they have from the terminators, we know that which string they are. So here, if I go from here, I know this node came from zero, from the string zero, and this came from the string one. So this came from both strings. This is a candidate for a good candidate for the maximum, the longest common substring. And in fact, it is the sequence ABA is the longest, because if you see the depth of this is 1 2 3. In fact, there's another one BAB that which is also comes from 0 and 1, and both uh, are the longest. In this case, we have two the same size. ABA and BAB are the longest common substring for these two strings. But uh, it's easy to see that the node with the highest, the deepest, the deepest uh, the deep string depth is the solution for this problem, and that we can traverse this uh, suffix tree in linear time, uh, and that would give a solution. Um, so if we can build the suffix tree in linear time, then we can solve the longest common substring in linear time. For now, let's just assume that we can do that, and in fact we can. We can build the suffix tree uh, in linear time. For now, let's just assume that, and then we'll get back to this uh, later on this presentation. Okay, let's talk about suffix array now. What's a suffix array? It's an array that sort all the suffix in the lexicographical orders. So um, let's take banana. What are the suffix? All the suffix, and remember the end terminator is always lower in the lexical order than the other characters. So in the lexicographical order, it starts with the terminator, and then in this case A again, and then B, and then N, and A, and A. So this is the lexicographical order, the dictionary order of this of banana. And we can see the suffix array as that first traversal of the suffix tree in the lexicographical order. So From here we go to the terminator that's not shown here. That first, and then go back here. The 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 lower lexicograph is A, go this way. Uh, Remember, it's the depth traversal, and then and so A is the first one. Go back, A and A, and okay, go back, A and A and A. The next one, go back, and then the next here is B, so bananas. After that, N NA and NA. So if I do a depth first traverse of the suffix tree in the lexicographical order, then I get the suffix array. The suffix array is just like an array with the number 6, 5, 3, 1, 0, 4, 2, which are the suffix in the lexicographical order. The the This is used for some computation. They kind of this data structure uh, is useful for because it somehow represents almost the same thing as the suffix uh, trees in a different way. So how do we build a suffix array in linear time? Well, we leverage radix sort. Uh, we have already seen this in class. So with radix sort, we can sort one part, and then the other parts already fixed. So, for example, I could imagine I have the odd suffix sorted. I can get the even suffix sorted, which a single radix step, and by just sorting the additional uh, character that was increased there. So okay, this creating the suffix array in ON time was an open problem in Stringolish for a long time. Some failed attempts like try to divide the suffix array in GSAs, which generalize suffix array, which is just a suffix array of a subset of the suffix. Like you do the GSA for odd suffix, and then the GSA for the even suffix and even positions. So like that for this string, I get the odd, and then I do the even, and then I try to merge odd and even, but this was problematic. Even if I could do like the odd recursively, and then with ON time get the even using the radix sort, then we didn't know how to easily and fastly merge them together, and that was an open problem for a long time. And then Kirkland and Sanders solved this problem in an elegant way. They kind of messed with the recursion. They divide the instead of using like half and half recursion, they divide the string. They divide the not the string, divide the suffix by the positions, depending on the positions in mod 3. So 1 and 2 mod 3 suffixes with positions 1 and 2 mod 3 would go to one GSA, and suffix with mod 0 with 0 mod 3 would go to the other uh, GSA. And so there's this proportional number, the one that has two third of the suffixes, and then I recursively sort this part, this two third, and and three things have to be done. I have to sort this two third. I have to sort the the one third. Find GSA for one, find the GSA of the lexical positions, the lexical order of the suffix sorted, and then I have to merge it. But defining, so imagine that I can do this, and the time recursion looks like this. For doing it recursively, I do this, and then if I can merge in linear time, and I show that we can, in fact, using the radix sort, uh, from the GSA 1 and 2 mod 3, we can just apply one radix step and get the GSA for the GSA mod 0. And that was very smart. And they not the what was the that the click they had was how this the way of dividing it also facilitate the merging. The merging was the crucial part here. So as I said, if you do a radix sort of the chart of the character, like the character the position, plus concatenate with the rank of the next character, right? The lexicographic position of the next character, and if we sort it, uh, once you get the, as I said, it's clear to see if I had it already sort, and I just move one character there. Uh, so I already have from the GSA for the 1 and 2 mod 3 suffixes, positions. I I with in linear time with this radix sort step, I get the GSA for 0 mod 3. And so recursion, two-thirds of the radix. Uh, in linear time, I get the other, the one third that was missing. Now I just have to merge it, and then I get the suffix array. Merge the two GSAs, I get the SA for the those whole thing. Uh, so and the merging. Imagine like I have a GSA for mod 2 that we know about. I know the positions for, I know the positions for 4 and 5. I know how they compare, and I also have the GSA 0 mod 3, two different lists that know how to compare the mod 3. Like I know here how compare 4 and 5, and how to compare, and in this I know how to compare 9, and then 12, and then, but these two different lists has different information. I have to merge them. So in that, and after three comparisons, like I compare 5 and 9, and then 5 and 10, and 6 and 10. So and then I get like 7, 11, but 7, 11 is again in the same list. Like 7 is uh, is 1 mod 3, 11 is 2 mod 3. So they are also in the same list. So with this we can, they're in the same list. In the same list, I know how to compare if they're in the same list. So we can uh, merge this for each three elements. Uh, I can merge with at most 3 comparisons, and so I go in the list. It was always almost as I had like 3 lists and 3 comparisons, and I move in the list. But in fact, I have 1 list, another list, and 3 comparisons. Uh, 2 here, 1 here. I can at most 3 comparisons. I can sort 3 elements of this, merge 3 elements of this. So in linear time, I go over all the lists and merge the both lists, merge them together, and this, along with the recursion I have shown here, uh, compute this recursively. Uh, compute the GSA for 1 and 2 mod 3 positions. Do the radix sort, and then merge them together. I complete and then merge them together. This 2 step in linear time, this recursively. I have this time constraint, time analysis, and this ends up building the suffix array in linear time. Let's continue. Now we'll talk about LCP arrays. What are LCP arrays? We have just talked about suffix array. LCP array is another data structure that help us to solve some problems. Specifically with the suffix array, the LCP array, we can build the suffix tree in linear time, and we can solve the longest common substring of 2 arrays, which is the subject of this presentation, in linear time with the LCP array of the arrays. So let's talk about it. What's the LCP array? Is the longest common prefix array. And we if you have like banana, the suffix in the lexicographical order are in this: a, anana, banana, na. So the number of suffixes would be 5, 3, 1, 0, 4, 2. Let's just ignore the first one. To build the LCP array, so a with Anna share 1 character prefix in common. So the first element of the LCP array is 1, and then Anna with an Anna 3, and Anna with banana 0, banana with NA 0, NA with NA 2, NA with nothing 0. So this is the LCP array. Let's compute it, and let's show how to compute it in linear time, because if you have to do all the comparison, there's many comparisons. If you do in the order of the suffix array, because like the Kasai algorithm assumes you have already the suffix array So you have the lexicographical order. We are computing only the LCP array. And if you do in the order of the suffix array, there are many comparisons you have to do. But the clever insight is that if you do the comparisons, compute the LCP array in the order of the suffix itself, start from 0 until 6, and then you have to do comparison only. You go through all the array only once. In fact, you go back a bit, you do like two comparisons for each of these uh, characters, and kind of two any comparisons, uh, but you don't have to go back and do more comparisons then. uh, so the clever side is this. So if I compute the LCP for a suffix, uh, so the LCP for the next suffix. So if I compute the LCP for let's say an N, then the LCP for an N, they share all the characters, but the first. So if I have already compared until here, I don't have to compare all the way back again. I go back one and compare again for the next step. So for doing this, what I do is start from the suffix array, I get a reverse array, which is we just rearrange the index order. So what is the first index here is 0. What's the index of the first element? I mean, is 0, 1, 2, 3, and then what's the index for the second here, which is 1. The index is 2, and then 5, and then 1, and then 1, and then 4, and then the last one, 5, is 0. So again, just reversing this. So the index of 0 is 3, the index of 1 is 2, the index of 2 is 5, the index of 3 is 1, the index of 4 is 4, the index of 5 is 0. So I have the reverse array, and I will compute first the LCP of 3 then. The LCP of 3 is here, 3 is here. I will compare strings 0 and 4. 0 is banana, 4 is nah. There's nothing in common, but I just have to do one single comparison, comparing B with N to get this. And then I go to the second one, which is 2. I will compute the LCP of 2. And the LCP of 2 is here. I have to compare a string, the suffix 1 with suffix 0. I have to compare banana with banana, and also just a single comparison. I can see that they are not, they share nothing common, sorry. And then I go computing the LCP of 5. LCP of 5, 5 is here. 5 I compare 2 with nothing, so 0 again. And then LCP of 1, LCP of 1, let's go here. 1, I have to compare 3 and 1. 3 is N, 1 is an N, N with an N. They in this case share 3. I have to do 4 comparisons to know that they share only 3. And yes, And here the next step that we can see that it saves comparisons, because when I go into the next one, uh, and we compare LCP of 4. Uh, for comparing LSP of 4, I have to compare 4 and 2. 4 is Na, and 2 is Na. But I have already compared Na, Na, Na. I just have to go back one, uh, and I will compare now only A with A, and then other with another one, and this saves me time, um, because I'm doing the order of the suffix, and then the comparison is 2. And again, now for the last one, I have computed the LSP of 0. I have compare 5 and 3. 5 is A, 3 is N. Compare A with N. In fact, I have already compared A with A. I just compare the last one, and I know, and then it's true. The same case again. Uh, as I had already compared, I go ahead and compare the next one. So in this case, I had uh, it's Kaiser grid. The Clever site allows us to traverse everything only once by going back just one at each step. Um, well, this ends the LCP array and how we compare it in linear time. And to conclude the presentation, uh, we first showed what is the longest common substring problem and how we can solve it using suffix tree by doing a bottom up traverse of the suffix tree. And this is one way to do, and to show that we can um, build the suffix tree in linear time. We introduce the suffix array and the algorithm to building the suffix array in linear time, and also the LCP array that can be computed in linear time from the suffix array using Kasai's algorithm. Um, I will not show here for brevity that we can also and we can build the suffix tree from the LCP array and the suffix array in linear time. In fact, you can traverse. We can traverse the suffix array without building it in linear time. But for the problem in question, which is the longest common substring problem, we don't even need to build a suffix tree. With the LCP array, if I do a linear scan on the LCP array, because the LCP array is the longest common prefix of all the suffix, and if I have the suffix for all substrings, for all suffixes of both strings in the case, and then I can find the longest common prefix of all suffix, which is in fact the longest common substring. For doing that, I just have to do a linear scan, but there's some constraints that have to be respected, because the LCP is not the longest LCP. The longest is the 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 greatest value in the LCP that comes from strings from suffix that are from when you compare different strings. Uh, so you must know that suffix, that one suffix is from one string and the other suffix is from other, and I just guess the maximum. There's some details there, but we can derive the longest common substring direct from the LCP array for all the suffix with both strings. and solve the longest common substring without even have to build the suffix tree in linear time. Uh, I have some reference I have included here in the presentation, some reference that I have used for building this. And this was my presentation on the top. I hope it has helped you somehow to understand these topics, and thank you for watching.